Alrighty. Hard one today. Excellent. Find the maximum sum of nodes, node values. There exists an undirected tree with nodes 0 to n minus 1. You're given a 0 index 2D integer array of edges of length n minus 1 where edges uv, edges I is uv, indicates that there's an edge between nodes u and v in the tree. You're also given a positive integer k and a 0 index array of non-negative integers nums, where nums I represents the value of the node number I. Okay. Alice wants to find the sum of the values of the tree nodes to the maximum for which Alice can perform the following operations any number of times, including 0 on the tree. Choose edge UV connecting the nodes UV and update their values as follows. Nums at U equals nums at U exclusive OR K, and nums at V equals nums at V exclusive OR K. Interesting. Choose any edge connecting and update their values. Update their values. Huh. Return the maximum possible sum of values can achieve performing any number of times. So U0, 1, 2. So edges 0 connects to 1, 0 connects to 2, 2 connects to 1, or 2 connects to 0, 1 connects to 0. K is 3. Alice can achieve 6 using a single operation. Choose 0, 2. So you're going to make this exclusive OR. So exclusive OR this and exclusive OR this. So edges 0, 2. Nums at 0. Okay, so the edge denotes the node. No. Okay, the nodes correspond to the index, and so the index of the nodes are 0 and 2, so that corresponds to 1 and 1. So for each of these nodes, you exclusive OR that value by 3. So 1 exclusive OR 3 is 2. So these become both 2. Well, so what's going on here? Node 0, node 1, node 2. Okay, so these values become 2. So it's 2, 2, 2. And then that's 6. Alright, let me remind myself exclusive OR. So exclusive OR is if you have, what is the exclusive OR symbol for Python again? Operator. Okay, it's the caret. This is going to be the caret symbol. Okay, so that's going to be 1 caret 1 exclusive OR of 0 is, so 1 XOR 0 is going to be 1. 0 XOR 0 is 1. And then 1 XOR 1 is 0. And 0 XOR 0 is 0. Pretty sure that's the thing, right? It's the truth table. Yeah, so exclusive OR is it's true when operands are different. Okay. Okay, so for 1 exclusive OR 3 in binary, it becomes 0, 1 exclusive OR 1 1, and then that becomes 1 0 in binary. Alright, and you're exclusive ORing k each time. Okay, so example 2, k is 7. So in binary, this is going to be 1 4, 2, and a 1. And if the nums are 2 and 3, so if I have 2 XOR 7, that's going to be 1 0 or 0 1 0 exclusive OR with 1 1 1, which is going to equal 1 0 1. And 3 XOR 7 is going to be 0 1 1 exclusive OR with 1 1. So it's going to be 1 0. No. 0, yeah, 1 0. That can't be right. 1 0 0. So this is equivalent to 4, and this is equivalent to 5. So it's going to be 9 if you do the operation once. Okay. And then what? And then, yeah, interesting. So if k is 3 here, which is binary, say 0 1 1, and I have 0 through 5, so it's going to be like 0 0 1 0 1 0 0 1 1 1 0 0 and 0 1 4 1 through 5 in binary. Exclusive OR with 0 1 1 each time. I don't think the order matters. Like A exclusive OR B is B exclusive OR A as well. So this is going to be 1 1 0 1 0 1 1 0. No, it's all zeros. Yeah, something exclusive OR with itself should be 0. And this one's 1 0, no, 1 1 1. And then 1 1 0. So that can't be right. First and last can't be the same, I don't think. This should be 0 0 1 0 0 0. No, what am I doing here? This should be 0 0 1 0 0 0 1 1 1, yeah, and then 1 1 0. All right, so this is equal to 2 1 0 7 6. So if these were originally 1, so you should probably switch the 7 to 6. Probably switch. Oh my god, I'm thinking of the nodes rather than the actual binary values in the indices. Or the actual values in the spot. Okay, okay. Oh. Oh boy. Okay, so anyways, if these are all 7s, then they're all 1s. So if I have 7, it says all 1s. And a 3, that's 1, 1 here. If I do the binary, if I did the XOR, then it actually lowers the value, so I probably shouldn't do anything. Yeah, so performing no operations, and there's 6 nodes, all 7s. Okay, so what to do here? The input generates a valid tree. Okay, so let's first create the graph. So they give us the edges, and we're going to create a default dictionary of lists. And then for every edge as a, let's say, A, B node in edges, so the graph of A is going to append B, and the graph of B appends A. It's undirected, so bidirectional connections. And I'll just, for now, print out that this works. And I'll return good old 0. Always liable. Always there. Graph B appends. Oh, oops. Right. Let's use the correct syntax here. Okay, so node 0 is connected to node 1 and 2, node 1 is connected to 0, node 2 is connected to 0, and the nodes represent the indices. Nodes represent the indices. So how would you go about determining whether or not you want to switch things up? So if you do an XOR, like if you do 2 XORs, it becomes itself again, I think. So if you have a value and you XOR with K, you get, let's say, value 2, and if you do value 2 XOR with K, then you get back value 1. So like if you're toggling stuff, it's always gonna like toggle between some value and that value, the XOR of that value with K. So each node will always be one of those two values, depending on how many toggles you have for the edges that you choose. So that kind of limits things. Okay, so how to determine which nodes to toggle. So you could keep track of all the benefit of toggling each node or toggling each edge. The benefit of toggling each edge. And if the benefit is above, well, if the benefit is positive, then you toggle it. That could work. The only issue then is so you keep track of say a heap of all edges and the benefit of toggling that edge. But then when you modify the graph and toggle an edge, then there might be some outdated stuff in the heap. There might be some outdated stuff in the heap. I mean, for every edge, there's only like for every edge, there's like at most, so for every edge, there is at most 4 kind of possible states where, let's say, A XOR K is equal to A is A, and B XOR K is equal to B. So for any edge AB, then through some number of toggles of the edges in the graph, it's going to be A. It's going to be A, like B, A, B, capital A, B, capital A, capital B. So there's always going to be only those possibilities. And for an original edge, that is AB, like one toggle, one toggle will make it like A, capital B. So what then? Oof. I wonder, could you? Okay, so since I don't really care about the number of times I toggle, right? I'm not counting the minimum number of toggles that produces the maximum sum. All I care about is the maximum sum, so it doesn't really even matter the initial values in your nums array. All you're caring about is the actual potential values in your graph. So if you start off with, although technically it does matter because at any given point, like you have like an odd or even number of toggles, and so it's not like you can fully uncap. Like it's not like what am I trying to say? It's not like you can choose if there's A, B, C, and capital A, capital B, capital C. Like you can just automatically choose capital A, capital B, capital C. It's not just. It might not actually be feasible to get every value to be its maximal value, to be exclusive or to its maximal value. But given that, I mean, you probably want to start with still trying to figure out, like, probably still want to start figuring out maybe the edge that you most would like to flip. Rank the edges somehow. Rank the edges by the benefit of flipping them. So if you have an edge 2, 3, so you have edges. So at any given time, so let's take an example here. I have 1, I have 0, 1, 0, 2. So I can flip either of those. And so I would know to flip 0, 2 because I could say that flipping 0, 2 would get me 3 or 2, 2 here. And flipping this one would increase it by 1, and flipping this one would increase it by 1. So the net benefit that edge flip would be 2. And so I flip it. But then so that means that my initial benefit flipping this edge, which was 2, 1. So if I've got a 2 and a 1, the benefit of flipping 1 would be 2. Flipping 1 would become 2, so the benefit there is 1. Flipping 2 would become 1, so the benefit of that would be -1. So doing a flip of the 2, 1 values has a net benefit of 0. And so I flip this, and this becomes a 2, this becomes a 2, this stays a 2. But even though this stays a 2, this does change the benefit of this edge flip. This edge flip would then become from 0 down to a -2, because flipping a 2 and a 2 becomes, which becomes a 1, 1 would be a -2 benefit. And then there's still the old benefit of 0 in the queue or in the heap. And if I encounter anything that is outdated, then I discard it. What if I do that? Yeah, what if I do that? Would that guarantee? So when I do a flip, look at the net benefit and maximize the net benefit. But does that always give me the optimal answer? So let me try to figure out. So one thing is, like, I have a heap that keeps track of the edges and the net benefit of flipping any given edge. I pull from the heap as long as it's a positive net benefit. I double check that the edge that is there is still valid, like it still has the same values. And if it does, then I do the flip. And once I do the flip, I add onto the heap any new edges that are formed whose benefit is positive. But does that guarantee a guarantee that I will always get the optimal solution. Just nothing in life is guaranteed. But how do I know? How do I know? So let's consider some possible simple node structures that might screw this up. So how does XOR work exactly in terms of, in general, the values that you get from XORs? Looks like you can almost treat K as the sum. 2 XOR 7 is 5, 3 XOR 7 is 4. No, I think that only works because 7 is like a 1 less than the power of 2, so it's all 1s. Yeah, I don't think that's in general how it works. 3 XOR 1 is 2. 2 XOR 2 is 1. 3 XOR 3 is 0. 3 XOR 4 is 7. And then 3 XOR 5 is 6. How does XOR work? Something I should probably have learned at some point. Or maybe I did learn it, but I forgot. Let's see. When to use XOR common computations. Swap variables, checking for opposite signs. XORing two numbers and checking the result is negative in term if they have opposite signs. Checksums, cryptography, detecting changes in data, swap variables. XOR can be used to swap the values of two variables without using a temporary variable. So A XOR B is B. How do you do that? A XOR B. What? XOR swapping variables. X, Y XOR X, Y X XOR Y. Oh my god, what is going on here? So X and Y. Huh. Interesting. So X is originally 1 0 1 0, so 6, and Y is 3, and then that becomes 7. No, I'm not even doing this right. 2 plus 8 is 10. 10, 3, and that's 9. And then 9, 3, and that's back to 10. And 3, 9, or 3, 10, 9, 10, 9, 10, back to 3. I think in this case, okay, it doesn't matter So you do a bunch of XORs, X, XOR Y, X, XOR Y. I don't think order matters in XOR, so I'm not sure. So you say X, XOR Y, Y, XOR X, or X is Y, XOR X, Y is Y, XOR X, and X is Y, XOR X. I don't think it matters. Yeah, there's no way XOR matters. Order matters there. Okay, interesting. In any case, no easy way of actually recalling that stuff. Okay. Okay, so let's just try it here. See if it works. The greedy approach. So say greedy approach. Calculate the benefit of flipping every edge if benefit is positive. Benefit is positive. Add to a heap. Process heap. Add new edges. So biggest benefit first. If edge is still valid at time of processing, flip edge and add any new positive edges or any new positive neighboring edges. Okay. All right. So how many nodes are there? Two times 10 to the 4th. Alright, so the number of edges is only n. So it's not like it's like kind of infinite branching, infinite connected. Okay, so let's go greedy approach. Let's go a heap and for every a, say, start in the graph, every a in the graph, and then start. Let's say the ends are equal to the graph at the start, so that's going to be a list. And then for every end it ends, let's say value 1 is the nums at this start is an index, right? Both these things are indices. So value 2 is equal to nums at this other index. And I say if this might be a little slow. Seems like it might be really slow. There's only so many edges. There's only so many edges. If, let's say benefit is equal to 0. Benefit is going to equal value 1 exclusive or, actually, let's say the current is, actually, so the benefit is going to be what I get if I do value 1 exclusive or with k plus value 2 exclusive or with k minus the current value 1 and the current value 2. And I say if the benefit is positive, I guess the benefit could be 0 as well. Ooh. Eeks. What do I do with the benefit of 0? Because if the benefit's 0, then there might be some. If the benefit is 0, but then it affects the other neighboring edges. If it affects the neighboring edges in terms of their benefits. Oof, 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 oof. What do I do with 0? Because then if you just do 0 and you process 0, then you can go infinite in your loop. Yeah, that's probably going to be a bug. I'm going to say here, the benefit is greater than 0. Then the heap is going to do a push of a tuple that is negative the benefit because I want to order by largest. So I want these heaps always get you the smallest. So if you want the largest, then you make that largest value negative, and then when you get the smallest from the heap, it's actually the largest, the opposite of the largest. And then the indices I'm dealing with. The indices and the values of indices. I think I need both the indices and the values of those indices. Start and value 1, value 2. Because they could possibly all be dirty later on. Okay, so that gives me my initial heap. Alright, let's go ahead and print this out. Interesting. So I have a net benefit of 6. That seems a little high. And shouldn't there be 2 6s here? For every edge. It does it twice for the edge, no? Okay, let me print out the heap each pass. And I'll say the value 1 and the start is what? Okay, so it doesn't seem right. So 0, 1 has values that are 1 and 2. So if you flip those, then the 1 becomes 2, the 2 becomes 1. So the net benefit should be 0. It should be 0, I think. And why is there 2 of them? 0 is connected to 1, and 0 is connected to 2. So if you did 0 connected to 1, actually, oh, interesting. The benefit of flipping the 1, 2 was 4. Okay, this is disturbing. Okay, so maybe I'm miscalculating this. No, okay, 1, 2 becomes 2, 1. 1, 2 becomes 2, 1. So why would this benefit be 4? This should be 2 plus 1 minus 1 minus 2, unless the order of operations here or something I'm screwing up on. Whoa, there was an order of operations issue? What the heck? Value 1 exclusive OR with K. This exclusive OR happens after the minus? After the plus? Okay, what is order of operations? Exclusive OR typically has lower precedence than arithmetic. Operator precedence. Gosh dang it, come on. Operations. Addition. Exclusive OR. On the same level as addition. I thought it was on a higher level. So it's doing this left to right. So getting this value, adding this value, doing this. Okay, wait, what's the Python order of operations? Yeah. Bias has a lower precedence than arithmetic operators. Or a higher precedence. Oh, really? So it was doing addition and subtraction before the inclusive OR. That's kind of weird, I guess. This really wasn't what I expected. Anyways, sure. So was this what I expected for the heap? Okay, so 0, 2, and so the net benefit of flipping these two is going to be either 0, 2 or 2, 0 is going to be -2. Okay, so that's fine. Okay, so I can say here, while the first element of the heap is less than 0, so the benefit is positive, the first element and also the value of it. Let's say benefit A, B, or benefit start end value 1, value 2 is equal to heap pop in the heap, and if still same in array. So in nums, so if the value 1 matches nums at start and the value 2 matches nums at the end, then I do the flip. So nums at start is equal to nums is equal to value 1 exclusive OR with k. Nums end is equal to value 2. Actually, maybe I should store this rather than recompute this. Maybe I should store it rather than recompute it each time. Whatever. Let's say value 1 what's a symbol I can use here? Say value 3 and value 4 are the complements. So value 1, value 2, exclusive OR with k. I should probably do this inside the if statement. Okay, so there's that. And for every connection to those things, I need to check again. So for end in graph of start, for every other in graph of start, recalculate this, right? Okay, so the other value is going to equal nums at this Nums at this other index. And again, the benefit is now going to be equal to other value exclusive OR with k plus value 3. Well, value 3 exclusive OR with k is just value 1. Value 1 minus the value minus value 3. Okay. And again, if the benefit is greater than 0, we push a new edge. So the start here is going to be start index. The end is going to be the other index, value 1. Can something exclusive OR with itself? Can something get the same value when exclusive OR? 0 exclusive OR 0 is going to be 1. Exclusive OR always gives you a different value, I think, right? 1 exclusive OR with 1 is 0. So when you exclusive OR, well, you're not exclusive OR with self, you're exclusive OR with k. But if you exclusive OR with anything that's non-zero, it changes it, right? So is A exclusive OR with anything equal to A? Is there an identity exclusive OR? Can't imagine that there A XOR 0 is A. Okay, so 0 is the exclusive OR identity. Can K be 0? K cannot be 0. So I think I can maybe store, instead of storing the actual current values, if I store the values that it would change to be, then I can get rid of some of these computations. So let's say value 3 and value 4 are value 1 exclusive OR with k, and value 2 exclusive OR with k. So if the complements is bigger than the sum of complements is bigger than the sum of the current values, I'm going to go ahead and store the complements. And then, so here I can say if the values currently are different, so maybe, should I call this value 1 or call this value 3? Maybe I'll call this value 3 and value 4, since that's what I called it when I put in tuple. So if value 3 is different than whatever's currently there, and value 4 is different than what's currently there, then flip. So I don't need this computation anymore, nor this. Yeah, because 3 and 4. Yeah, I don't think I need those computations. So for every other neighbor for the graph of start, wait, I actually do, what am I doing? I do need to flip that. Maybe I flip it at the end actually. So for every other neighbor in the graph of start, the other index is, the other is the other index, other values, and then the other. benefit would be so let's see other val 2 okay, other val 1 is that, another val 2 is other val with k, so the benefit would be other val 2 plus, so if I flip again, then it goes, value 3 goes back to value 1, so plus value 1 minus other val 1 minus val 3. This is getting a little hairy. And then the benefit there would be going from start to other. Start would flip back to value 1. Other would flip to other value 2. I think there's too many parentheses. That closes that one, that closes that one. Why is there only 2 benefits? Oh, wait. There shouldn't be parentheses there. Okay. And then doing the same for the other one for every other in the graph of end. I think this all could be kind of reproduced, except I want to use end here, and I want to use value 4 and value 2. So this should be going back to value 2. And then I actually do the flip here. And then maybe after all this, I return the sum of the nums. Other val 1. Index out of bounds, heap is 0, 0. Okay, actually, while heap is there. Okay, so this small test cases worked. See where it fails on the bigger test cases. Or maybe it's just too slow. Yeah, okay, got through 2 other test cases. Alright, so 24, 78, 197, 44. K is 6. Okay, so let's see what might be happening here. I'll print out the heap. After it's created here. Alright, so what's going on? -12, -12, -4, -4, -4, -4. So there are a total of So there's like 3 edges that are originally there because every edge kind of has a duplicate thing that adds to the heap. There's 3 edges that are initially there whose flip is positive. So I start by flipping the biggest one, and then what? So if I do a flip, then we'll print out the heap after each flip. And let's have a flip counter. Increment the flip counter. And print out the flip count in the heap. Okay. So that still doesn't seem very readable. Alright, so flip 1 generates us -73. And then flip 2 generates -33. Flip 3 generates -35. Flip 51. -47, -31. -59. Whoa, this is a lot of flips. This is a lot of flips. Some of these are duplicate. I think one way to remove the duplicates would be if the indexing is in order, then I do it. If it's not in order, then I don't do it. So let's say if for the graph start and for the end, if the end index is after the start index, is before the index. If the end index is before, then just skip it. I think that should get rid of some of the duplication. I need to do this in multiple places actually. So here as well. If the other index is, well, that's not true, right? That's not true actually. Well, this one is true because I do go through every start end, so I go through both sides of the edge. But this one, I don't necessarily go through each side of the edge, so I have to do this one completely. Yeah, there's gonna be some duplication here because I don't know that I do all the passes. No, it's fine. It's fine. It probably does minimal. Is there a way to prevent duplication in that area? Yeah, it's fine. So you flip 1, 2. Okay, I think I need separate lines for this. Okay, so you have flip. You have 56 flips, 58 flips. Some of these are redundant. A lot of them seem to be, well, yeah, I mean, a lot of them seem to be redundant after some point. But any case, it increases to 260. It doesn't increase past that. Although if it increases to 260, it seems like the sum of these things should have been higher. I guess if it's flipping the sum of 1273. So an initial heap is this. Print. I need to keep track of the sum actually. Let's say the sum of nums and flip count and the new sum nums. Okay. So initially it's 244 and there's a negative 12, so I should flip that and it should become 256. There's a negative 73 at the top. Eeks! 256 didn't increase at all. So initially try to flip indices 0 and 2, which currently have 24 and 1, and made it 30 and 7. So this becomes 30 and that becomes 7. Zero, 1, 2. Yeah, so this becomes 30 and this becomes 7. And then it's going to say that, why is this thing still 0 and 2? Okay, there's something really off here. So value 3 and 4, the complements of, okay, maybe I should say A, B, and capital A, capital B for the flip values. So let's say A is value 1, B is value 2, complement of those is capital A, capital B. A XOR K is capital A, B XOR K is capital B, and the benefit is going to be capital A plus capital B minus AB, lowercase. Benefit's positive. And then store into it the changed value. Okay. Well, there's a heap in the whole heap. There's positive. Pop from the heap the value that you're changing it to. If the value that you're changing the first one doesn't equal what currently is there, the value that you're changing the second to is not there as well. I could maybe make this slightly less indented, say if A equals nums at start or B equals nums at end, continue, and then just do the negation there. Slightly less indentation. I think this thing needs to be no, I think that's right. Okay, so there's an other value. Let's say this is, yeah, this other value, and let's say the other value is C, and so doing the XOR is going to be capital C. And the benefit would be capital C. So if I did another flip where the current value is going to be capital A, then I should be going back to lowercase a minus the original C minus what's currently going to be there after I flip. So it's going to be, actually maybe I should do the flip now to not confuse myself. So nums at start and nums at end be equal to capital B, capital A, capital B. Okay, so now check for the new benefits. So the new benefits would be for everything that's check to start, try to flip it. So capital A goes back to lowercase a, C goes to capital C. So minus A minus C. The benefit is still greater than 0. Yeah, the benefit greater than 0, then these two indices, start index would change to lowercase a. The other one would change to capital C. Okay, and then for everything next to the end, this is going to be C is equal to that. Capital C is equal to, this should be lowercase. The benefit should be capital C plus, in this case, B minus lowercase c minus capital B. If it's positive, add it. This thing changes back to B. This changes capital C. Okay, somehow it's still modified. Okay, I did change some of these outputs. Still confusing what's changing. Still confusing what's changing. So 0, 2. So 24 XOR 24 XOR 6. What? 24 XOR 6? What is going on here? For answers 30. Oh. How did the first result in Google give me a calculator that didn't work correctly? Maybe it was because it's hexadecimal. Okay. 24 XOR 6 is 30. 1 XOR 6 is 7. So then process it and becomes, did my answer change? So it went to 256. Now it's saying there's a 61 that's benefiting. And 61 is the benefit for flipping 0 and 2 again. That just cannot be right. Wait. So if I have 30 XOR 6 is going back to 24? 30 XOR 6. Yeah, okay. So it's just not doing it right. Huh. So it's flipping the nums at start and nums at end to the A and B. Let me go ahead and just print out the nums array at that point. So you're flipping 1, or see, so yeah, it becomes 30 and 7. Alright, gotta take a break. Alright. Let's see here. So if you have 0, 2, so numbers are 30 and 7, and that modified the correct spots, replacing the 24 and 1. And then you did another analysis. And somehow you're getting the fact that if you try to flip 0 and 2 again, you get back to 97 and 1. Those aren't the correct indices. 90 and 1. Nums every other index connected to the start index, where the start now currently has cap A. And then C is going to be the value there. And then capital C is the value XOR K. The benefit is changing it to capital C, lowercase a, minus lowercase, minus capital A, minus C. So somehow 0 and 2 are still being messed around with. 0 and 2. 0, 1, 2. Why? So if you flip 0 at that point, it shouldn't be 97. It should be like, I'm not even sure. 97 XOR 6. Three. Why is 97 in play here? How are those the two indices that are being start and end index? Start and end index. Start and end index. For every other index. Okay. Pushing 0 to 97 1. 0 to 97 1. Why? A, capital A, C, capital C. $30 and 7 are correct. 97 and 1 don't seem correct at all. So 97, so lowercase a, capital case A. Did I never define what A is? Oh boy, I never defined A. I just assumed that it was working. Oh boy. Okay, that's stupid. A, B is nums at start and nums at end. If that or that is occurring, then they're no longer complementary. Oh my god. Silly. Silly, silly. Let's see what other test cases this fails. Definitely not going to be the first or the last. Okay, so let's go print out the heap after each stage and maybe the nums. Let's see what happens there. So close, but not fully there. Why didn't this flip at all? Why didn't this have any output? What? There's no flips? Oh, really? Interesting. I see. Okay, So this is one of the ones where I was thinking might be an issue in terms of like the greedy approach doesn't necessarily traverse all possible scenarios. So here there was probably like an initial flip that was negative that allowed future positive flips to occur. Yeah. Okay. So how to detect that? So the initial positive flips. The initial positive flips. Am I doing this all? Just approaching this all wrong. How many colorings are there? So let me think about a simple graph here. So let's say A is connected to B, connected to C, connected to D. So I can do A, let's say B, C, D. Or I can do capital A, lowercase b, capital C, lowercase d. So I flip this middle two, and it comes capital B and capital C. And I flip those two, and it comes capital A and B. Could be maybe capital A, lowercase b, lowercase c, capital D. Be lowercase a, capital B, lowercase c, capital D. All capitals. What is the connection here? What is the connection here? Any given time, the parity, whether or not something is on its original value or its exclusive board value. The parity is even for the whole graph. Think of this in terms of odds and evens, or on and off. So I can make 0, 0. This is not going to correspond. It could be something 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1. These are, that's 3. That's 5. That's 4 plus 8, that's 12. Wait, sorry, this is 3, this is 5. This should be 15. is 12. Let the 1010. Could I really get to 1010? I guess I can, right? So I can toggle the first two, toggle the next two, toggle all four. So this is 8 plus 2, 10. Can I do any? There's no way, right? There's no way I can do any. How would I do any? I don't think I can toggle. I can definitely get to 1001. So that's 81 times 9. It's an even number of bits that are on. Even number of bits that are on. The placement of them doesn't matter. But it's every possible set of them being on. Okay. Every possible set of them being on. And then for any node, they're going to be Is it? Huh. Interesting. I think that seems right. I don't think I'm not even sure that the connection matters. The order, the way that it's connected matters. Because it could all be. What if it's connected like? What if it's connected like? Connected like this. So. Yeah. Okay. I'm gonna. It shouldn't be very hard to test this hypothesis. It's basically looking at your array and then seeing the benefit from toggling two things at any given point. Seeing the benefit of toggling any two bits. Any two bits. So if the top two things that can be toggled, if the top two things, yeah, okay. So think here. How should I approach that? Actually, so let's say this is like. So this is like 1, 2, 3, 4, 5. It's A, B's. Could I get like any arbitrary two of these to be on? So if they're all operationally, I can make this thing on. This is 1, 1. And this thing on. This 0, 1. Yeah. And if I can, let's say I want to make. I can't ever make 3 of them on. I can make like 4 of them be on. Yeah. Okay, so I can make any even number of them on. So every time I switch 2 on, it changes from its current value to its value exclusive of k. In which case, I need to have I could probably sort the nums. Can I sort the nums? I think I can sort. What am I sorting? The benefits of every toggle. The benefits of every toggle. Okay. So I guess why does it matter if it's a graph at that point? Or it's this graph is just tricking you. You don't actually need the graph. Let's say that one ends here. Okay. So for every value, there has to be some way that graph actually, the graph is all connected. Yeah, maybe the graph's not really necessary if it's just guaranteed to be all connected. It's a tree, so it's not cyclical. So there's no. Yeah, okay. So let's say for every nums in nums, let me go ahead and just have a heap, I guess. No, I don't even need a heap. Okay, I think it's just going to be. I think I just have the benefit, right? Benefit is going to be an array. So for every value in nums, the benefit would be benefit.append benefit.append. Okay, let's say this is benefits. Benefit of switching it would be equal to the value exclusive order k minus the value itself. And then benefits append this benefit. And then I can sort the benefits. And then for every two in my, this is, that means we sort this in first. So for index in range of n, where n is the number of nums, going up by 2, so from 0 to n going up by 2, n minus 1, if the benefit of the first benefits of the first plus the second, if I toggle it up, if I toggle it, then it's greater than 0, then I'm going to do the toggle then. So actually I'll have the current sum is equal to whatever is currently in nums. Then I'll apply the benefit, which is change. Index and index plus 1. Then it stops. Actually, yeah, then it stops at some point, maybe. Oh, baby. Guess it didn't work that way. So this one is a simple one where you should be toggling both. Is the benefits? What is this thing showing for the benefits? Seven and 7. Oh, is this the same issue as before? Okay. Stupid in terms of order operations, I think. Huh. Well, that's interesting. It works, and somehow there's a faster version of this. This seems pretty darn fast. Do you not sort? Because if you don't sort, then no, you have to sort, right? You have to figure out where the line of demarcation is, where you want to not change everything else. Huh. I mean, you can keep track of your smallest, you can keep track of your, so you can assume that you always switch, and you can assume that you always switch any negative benefit to become a positive benefit. But then you do a final calculation as to whether or not the smallest switch is actually beneficial, because the smallest switch would require another switch, and if it's an odd, then it might require another switch that's negative, and that switch that's negative is worse than the switch that's positive, then you don't make that final switch. So actually, okay, so I can see how this might be improved without sorting. I think it might be done more fast. So I don't need the benefits actually. Say my answer is currently going to be the sum of all the numbers. And then for every value in those, I'm just going to say I still need to calculate benefit. Is equal to the toggle of the value minus the value itself. If the benefit is positive, so you need to have the smallest benefit, smallest positive and smallest negative. So small positive, I'll say 0, small negative is also 0, and I'll say the count of toggles is also 0. So if the benefit is positive, the counter goes up, and the small positive is equal to the min of this value and what currently is stored, and also the answer goes up by this benefit. Else small negative smallest negative could be the maximum of the small negative and this benefit. And then afterwards, if the count is odd, then I know that I need to have either reverse the last toggle, reverse the last small benefit, or not. So if the count is odd, or yeah, if the count is odd, then the smallest, if the smallest positive is bigger than or equal to negative of this is greater than the negative of the smallest negative. So overall it's a positive benefit, then I need to do that switch. So answer plus equals the smallest negative, else I remove it because the smallest negative is just too much. Answer minus equals the smallest positive. Fudge! Why didn't this one work? The smallest negative cannot start at 0. Yeah. Let's go float negative infinity. No, the smallest positive can't start at 0 either. Float positive infinity. Okay. $72% for that? Oh, I didn't even sort it. What the hell, man? Guess there's a bunch of if statements here. I mean, this is pretty darn. Guess I could maybe do answer starts with 0, answer plus equals answer plus equals the value plus answer plus equals this seems extremely how would you do need to take into account the number of times that you're adding. Sum of nums seems so fast. Smallest positive starts big, smallest negative starts small, count starts at 0, calculate the benefit. So you could say that either the answer increases by the value x or k, else the answer increases by value. That gets rid of your statement about, I don't know if this knows any better. So say other value is value x or k. I guess if the other is bigger than the value, then the answer increases by the other, else the answer is increased by the value itself. Answer starts at 0 in that case. The smallest positive is going to be I guess this is still other minus benefit, other minus value, other minus value. Smallest negative. Yeah, other minus value. Sure. Alright, creeping up there. Count is odd. Count is odd. Then oh. Do this without if statement. The smallest positive is bigger than the smallest negative. And take away the smallest, then add in the smallest negative. Otherwise, remove away the smallest positive. I guess maybe do something like this. Turn answer plus the smallest negative. Else, return answer minus the smallest positive. Some of that. Answer plus smallest negative, answer minus smallest positive. Misspelled return. I actually screwed this up with that simplification. What's going on here? Oh, it's, well, no, what's going on? If, well, what happened to the if statement? Yeah, whoopsie. The smallest positive is bigger than the negative, smallest negative. Return these. I think maybe I prefer it like this actually. If count is even, then return the answer. Otherwise, you have one last if statement to go through. Okay. Misspelled return again. Alright, slower than last time. I think I'm done. Okay. I am done. Alright, this is an unusual one. Pretty darn unusual. It's one where you just do the math, I guess. So, summary. So this is more like this kind of fast solution involves basically understanding kind of graph theory, graph slash math. Slash math behind how XOR will affect the possible how XOR will affect the values. So for any since XOR will toggle the values 2 at a time, it's never possible to switch toggle values 2 at a time, which is the nodes since edge has 2 nodes that will toggle. It's never possible to switch only one value, but also it's possible to switch any even number of values through some combination of toggles. And that was like, I figured that out by example, if you have, let's say all nodes be zeros to start with, you can come up with like any number of toggles that you make. 1 0 1 0. You can come up with any number of toggles that you make where you kind of swap any 2 adjacent ones, where the 2 adjacent ones really end up being, you can toggle any 2 of the bits, but the number of bits that are on always be an even number if you consider it all starting off. So applied to this graph, which these could apply to this graph, simply determine the kind of benefit of each individual toggle. So this is the value XOR k minus the value. And if it's positive, change it. And then since there has to be an even number of switches, keep track of that, of the count and the kind of smallest positive and negatives switch, and kind of either reverse or combine those smallest switches if there is an odd number of toggles. So that's this thing here. For every value, the other value is computed. If the other value is better than the current value, then you're going to switch it. So you're going to add on to the answer, where the answer is the sum of all values, the other value. You keep track of what's the smallest positive value you've seen so far. Otherwise, if you don't switch it, then you keep track of the smallest negative value you've seen so far, or technically the biggest negative value, which is closest to 0. And again, you still add the current value to the answer. Then afterwards, you figure out how many you did, how many kind of switches you did. If it's an even number, then it's fine. If it's an odd number, then you need to figure out whether or not it's better to reverse it or combine it. So if the positive is actually better than negative, then you combine it. So you add in the negative. If you see that's not, then you just remove that last switch that you did. I think there was another one that I came across that was very similar to this, the LSAT XOR, where it's just boiled down to math. I guess it's lucky that I figured that out here. Time complexity, this is going to be O of n, where n is the number of values in nums array. This is a one-pass thing. Yeah, it's just one pass. You go through all the values, you do that calculation. Now, the more interesting one, I think, was actually doing that heap that I started out with, and that was like, that was O of edges, and every edge you need to count to calculate the node value. So I think it's probably O of nodes plus edges there, something like that. Could be node times edges or node plus edges. So you go through each edge once. Yeah, it might be nodes plus edges. Airspace. Did I actually use any arrays? I actually didn't. Although if I did calculate the benefits array, that was O of n. But this is no additional data structures needed.